What's up, folks? This is Ref Bari, Brown University physics graduate student. Today, I'm going to show you something amazing. I'm going to show you how to calculate the rotation of the Earth using only pen and paper. Now, this calculation is going to be long. It's going to be about 45 minutes long. But by the end of this calculation, you will be able to detect your exact location on the Earth just using pen and paper. So let me just set some expectations here. What do I mean by detect your exact location on the Earth? Here's what I mean. This is the planet Earth. And the Earth happens to be spinning. The Earth is rotating around its axis with some angular velocity, omega. And this angular velocity is about 10 to the minus 5 radians per second. So that means every single second, the Earth is turning, it's rotating by about 10 to the negative 5 radians. Okay? Now here's the thing. We can actually detect the rotation of the Earth from the ground here on Earth. Let's say you're a man or a woman right here on the Earth, and you're on the surface of the Earth, and you want to detect the rotation of the Earth somehow. How do you do that? Well, one way you can do that, one of the most amazing ways you can do that, is by using something called a Foucault pendulum. Okay, what is a Foucault pendulum? Well, what is a regular pendulum, first of all? A regular pendulum is some kind of an object with a fixed support, okay? So let's say this is the background of the pendulum, and the pendulum has some rope that connects it with the support, and the pendulum is bouncing back and forth. It's oscillating back and forth, right? Simple harmonic motion, that's all a regular pendulum is. So it goes to the left, and the pendulum goes to the right, then it goes to the left, then it goes to the right. That's all that a pendulum does, right? So on and so forth. It goes left, right, that's it, right? That's what a regular pendulum does. Now, a Foucault pendulum is special. Here's what a Foucault pendulum does. Now, I have to upgrade from 2 dimensions to 3 dimensions. For a long time, I did not understand the Foucault pendulum, but the idea behind it turns out to be beautifully simple. Here's the idea. Let's say that the fixed support for the Foucault pendulum is right here, okay? Once again, it's almost like you have a regular pendulum, but now, and by the way, there's no friction, nothing like that. So now, the pendulum, a Foucault pendulum, it's going to move, oscillate from left to right, okay? So it ends up here, okay, just like a regular pendulum. But now it's going to do something different. Just watch very carefully. First of all, notice that the plane that the pendulum is oscillating in is some given plane, okay? Okay, let's say that's that 2D plane that the pendulum is oscillating in. Now, a Foucault pendulum, which is, by the way, exactly similar to a regular pendulum, but it has some special constraints that make it very sensitive to the rotation of the Earth. A Foucault pendulum, what's going to happen is that its plane of rotation is going to rotate slightly. Okay, it's going to rotate by some angle. Okay, so you can see that I have now drawn a new plane of rotation, and now the Foucault pendulum is going to oscillate not in its original frame, but in this new plane of rotation. Now, I understand that it's very difficult to visualize this just from a blackboard picture. So let me show you an actual experiment that uses a carousel and a tripod on a carousel to demonstrate the effect of a Foucault pendulum. Let's take a look at that. What you're watching in this video is a time lapse of a Foucault pendulum. So first of all, what makes this pendulum so special? What makes it so sensitive to the Earth's rotation? Well, it is almost exquisitely designed so that there's no friction in the bearings of the pendulum, in the rope, no friction in the tension of the rope, none of that. So that the pendulum is hypersensitive to the rotation of the Earth. And how do you see the rotation of the Earth in this pendulum? Well, watch as the dominoes slowly flip over and the plane of the pendulum's rotation slowly changes. Now that you have a more intuitive understanding of the Foucault pendulum and how it can calculate the rotation of the Earth, let's calculate the period of a Foucault pendulum. Let's do it. Now the first step is to warn you, okay? You got to be pretty decent at math and physics to do this calculation. It's a It's a long calculation. There's no way around it. But at the end of this calculation, you will see the power of pure thought to explain things in the physical world. Okay, just by thinking carefully about how the Earth rotates and how a Foucault pendulum oscillates back and forth, we can just, using pen and paper, create an equation that describes something in the real world. And that is extremely powerful, extremely powerful. So let's get started by establishing a reference frame, establishing the situation. So where's my eraser? So here's the situation. We've got the planet Earth right here that's rotating at some angular velocity omega. And let's consider a point on the surface of the Earth. Let's consider that point, for instance. This angle between the axis of rotation and this segment connecting the center of the Earth to the surface, let's call that angle theta. Okay, very good. And let's consider the basis vectors on the surface of the Earth. First is going to be this basis vector. Let's say that's the z direction, or some may call this the radial vector that's pointing radially outwards. I'll just call it z for now. Let me erase our tiny character on the surface. And we have a vector x, which is to the south. Okay, you can imagine you're standing over here, and down would be south, and minus x hat would be in the north direction, and z hat is in the up direction, mg is in the down direction, down as in pointing to the center of the Earth, and the y hat direction is going to be into the page. If you want to ask why the y hat direction is into the page, well, then you can just do a simple cross product. X cross z, or z cross x, up to a minus sign is y hat, so you can simply do z cross x. You can see that y hat indeed points inside the blackboard, which is why I have drawn a cross over here. Okay, so that's my coordinate system right here. So what am I going to do now that I've established my coordinate system? My first order of business is to write down Newton's second law. Now, for many of you, you're going to say, well, that's pretty simple. That's simply F equals ma. And that is true. But we have to actually modify Newton's second law for rotating reference frames. And that's where the weirdness of rotating bodies kicks in. Okay, so there's going to be 5 terms. Okay, let me just warn you before I write it down. There's not going to just be F equals ma or F equals mg. There's going to be 5 terms in Newton's second law in a rotating reference frames. Those 5 terms are going to account for different effects. Let me first explain these effects that we're going to account for. Okay, so imagine that you're on the surface of the rotating Earth. Here's the Earth rotating around its axis. As the Earth is rotating, you will feel what is a fictitious force known as the centrifugal force. And that force will tend to kick you outwards. Okay, that's what you will feel, as if you're being pushed away from the Earth. Okay, it's going to actually decrease your weight. So that's the centrifugal force. That's one of the forces that we have to account for when we write down Newton's second law in rotating reference frames. That's one. Okay, what's another force? Another force is the Coriolis effect. That Coriolis effect is also due to the rotation of the Earth. It's what makes hurricanes spin clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. I might have them switched, but that's the essence of the effect. So when the Earth is rotating, that creates that special Coriolis effect that essentially makes vortices spin one direction on the northern hemisphere and another direction in the southern hemisphere. So that's our second effect that we have to account for. That is the Coriolis effect due to the rotation of the Earth. A third effect that we have to account for is the acceleration of coordinates. Okay, in rotating reference frames, let's say you have some kind of a reference frame A and a second reference frame B, which may be accelerating with respect to A. Okay, and let's say you're trying to consider the position vector for a point over here, a point that is, let's call this point C, a point C that is in reference frame B. Okay, then if reference frame B's origin is displaced from reference A's origin, then we're going to have yet another term due to the displacement of the origin and the acceleration of this point. Okay, I call this the displacement of origin term. Displacement of origin term. Okay, very good. So I realize that you may not see everything I wrote. There you go. So now we have the 3 of our 5 terms. The 4th term is actually very simple. The 4th term is simply external forces. Okay, so of course external forces have to be accounted for in Newton's second law. That's what the entire law is about. So we've got external forces to account for, centrifugal forces to account for, displacement of origin, acceleration forces to account for, the Coriolis effect to account for, and the last effect comes from changing the angular velocity of an object. Now, the Earth's change in angular velocity is approximately 0. Okay, to a very good approximation, the Earth's angular velocity does not change, or at least to a good approximation, it does not. But if you have an object whose acceleration angular velocity does change, then you have yet another term. Okay, so this is called the change in angular velocity term. So if you have some angular acceleration, this term will exist. Okay, this is the angular velocity change term. Okay, so these are the 5 different terms that exist in Newton's second law for rotating reference frames. Okay, so let me write each of these terms down one by one, and then we're going to combine them to produce Newton's second law in rotating reference frames. First, the external force. That's very simple. That's simply F external. Okay, that is the first contribution to Newton's second law in rotating reference frames. The second contribution comes from the centrifugal force. Okay, let me come over here. The centrifugal force has what appearance in the rotating reference frame for Newton's second law? Well, this is the one I always mix these two up. So, okay, so the centrifugal force has the appearance of omega cross r. Okay, so that is how the centrifugal force term looks like in Newton's second law. Now, there's a way to derive this. In fact, I'm going to do the derivation in a second video. But is there a way to intuitively understand why the centrifugal force term looks the way it does? And the answer is yes. Yes, there is. In fact, there is a very intuitive way to understand why you have omega cross r here. The reason is this. Think about it like this. Imagine you have a ball, and you're going to, and okay, by the way, the Earth is rotating over here along this axis, angular velocity omega. So you're going to drop a ball from above the North Pole. Okay, so what's going to happen? Well, if the Earth was not rotating, the ball would fall straight down. Okay, but if the Earth is rotating, we know, of course, that the Earth is rotating, it will seem that the ball is actually displaced. Okay, it will seem like the ball has actually been moved, pushed aside. Okay, why is that? Well, here's why. Imagine that you're on the Earth, okay, and maybe you're playing a game of frisbee with your friend up on the North Pole. So here's your friend on the North Pole, and you are on the equator, and you'd like to send a ball up to your friend. Well, the Earth is rotating, let's say, in this direction. I don't know what that is, clockwise, counterclockwise, doesn't matter. So let's say you'd like to send a ball up to your friend. If the Earth was not rotating, you would simply send the ball straight up. But since the Earth is rotating, if you send a ball straight up, by the time the ball arrives at your friend's position, your friend will be over here. Okay? So the ball will actually be behind your friend's position. So that means if you switch to the rotating reference frame of your friend, then it will look like the friend has stayed in the same place, but the ball has been deflected to the left. If that doesn't make sense, think about it slowly, carefully. This is not trivial. Okay? Think about it carefully. You send a ball up to your friend. If the Earth was not rotating, your friend would just receive the ball. But the Earth is rotating. So by the time the ball reaches your friend's location, your friend has advanced. He has moved on. And so that means the ball has missed your friend. But now if you switch to the rotating reference frame of the Earth, then it looks like your friend was in the same position. but the ball was deflected to the left. Okay, so think about that, and if you believe that, then this term will make sense. Why will this term make sense? Because now we consider a second thought experiment. Here's the Earth. This is the Earth. Now we will drop a ball on the Earth from the North Pole and from above the equator. Okay, so this is the equator. Now consider this. What will happen as I drop the ball from the North Pole and as I drop the ball from the equator? Will the same thing happen? Will both balls just fall to the ground? No. Different things will happen, in fact. Because remember that the Earth is rotating with some angular velocity omega, right? So what does that mean? That means, think about it, the pole, look at the North Pole. The North Pole actually does not have to rotate. Does that make sense? Think about it. The North Pole of the Earth does not have to rotate. What do I mean by that? Well, look at the equator. Think about a point on the equator. Let's say, consider this point. In exactly 24 hours, this point has to go all the way around the circumference of the Earth and come back to itself. Now consider another great circle around the Earth. Let's consider this point. In exactly 24 hours, it has to traverse this entire circumference, return to itself. But as I go higher and higher in latitude or longitude or whatever it is, as I go higher and higher, the points have to traverse less and less of a circumference until I ultimately reach the North Pole, where this point, this extremity, does not have to travel any distance to achieve a rotation, an angular velocity of omega. That means the North Pole, at the North Pole, effectively, there is no rotation, right? So that means the ball that I release from the North Pole will actually just fall straight down. Whereas the ball that I release from above the equator, it's going to look like it gets displaced due to the rotation. There's going to be some effect due to the rotation of the Earth for the ball that's released above the equator. So now think about it like this. I just mentioned that this angle theta measures essentially where you are on the Earth. Theta is 0 if you're on the North Pole, and theta is pi over 2 or 90 if you're on the equator. Now we know that the effect of the Earth rotating is maximized if you're on the equator, whereas there is no effect essentially if theta is 0 if you're on the North Pole, because at the North Pole does not have to rotate to achieve an angular velocity of omega. So what function can you think of that goes between 0 and 1 as we vary theta from 0 to 90? There's only one function, sine of theta. And indeed, you can see what this expression is saying is exactly that. It's omega r sine theta, right? So what is omega r sine theta? Well, let me show you. So let's erase this picture over here. Here's the Earth once more. Here is the equator. And at the North Pole, of course, the direction of the angular velocity of the Earth is straight up, right? It's rotating around this axis, but the angular velocity vector is pointing straight up. And at the North Pole, the radial vector r is also pointing straight up, right? So omega is parallel to r, right? So if omega is parallel to r, then omega cross r is simply 0. And that reconfirms our intuition that sine of 0 should indeed be 0. In other words, at the North Pole, there should be no effect of the rotating Earth. Whereas at the equator, the effect of the rotating Earth should be maximized. And so that's why the Coriolis effect term looks like this. It looks like omega cross r. This omega cross r is simply controlling where you are on the surface of the Earth. The closer you are to the equator, the greater, the maximized, the effects of the Coriolis effect are going to be, and the centrifugal force. Okay, so that is the picture. So that is the centrifugal force. That's the motivation behind why the centrifugal force term looks the way it does. Hopefully that gives you some idea about why this term is written the way it does. Of course, we can derive it, and we will derive it in a future video, probably the next video. But before we do that, I mean, the calculation is going to be long enough without a prior derivation. So let me just motivate why this term looks the way it does. Okay, very good. The next term is going to be, let's talk about the displacement of origin term. Actually, let's take out the Coriolis effect term while we're at it. So Coriolis effect term, what does that look like? So the Coriolis effect term has the effect of 2 omega cross r dot. Let me make sure I wrote that down correctly. 2 omega cross r dot, indeed. So this is the Coriolis effect term. Now this looks exactly like the, not exactly, it looks similar to the centrifugal force term. Again, you can see an omega cross r, but here this is an r dot. Okay, r dot is the velocity. Okay, we're no longer talking about the position, the radial vector. We're talking about the velocity vector of the Earth as it's rotating around its axis. Okay, so this is a little bit different, but you can kind of use the same intuition, right? Again, you can see an omega cross r dot ish term for the for accounting for the rotation of the Earth. So that is the centrifugal force, and that is the Coriolis effect. Those two terms are gone. Let's talk about the angular velocity term. So the angular velocity term looks as follows. We have, let me make sure I do not write it wrong. So that's going to be omega dot cross r. So you're starting to see all the possible permutations of omega and r being crossed together. We've got the change in angular velocity crossed into the radial vector, the change in the radial vector crossed into the angular velocity, and just the angular velocity crossed into the radial vector. So we've got basically all the possibilities, all the different ways that omega and r can interact with each other are combined into this total Newton's law for rotating reference frames. So this term essentially measures whether the Earth's angular velocity is changing, and which, to a good approximation, it is not. Right? So that is that. Okay, very good. So we have accounted for this term, this term, this term. Let's talk about the displacement of the origin term. Displacement of origin term. So this term is simply going to be of the form d squared c dt squared, where c is the distance from the origin of one reference frame A to the point that you're measuring in reference frame B. Okay. So that is that, and our final term is due to the external forces, any external forces acting on an object. That is just going to have the form F external. Okay, so now let's try to understand which one of these 5 terms. Actually, let's first write down the entire force law, all of Newton's second law in rotating reference frames. So Newton's second law in rotating reference frame is going to look like F equals ma, where I will write A as r double dot. And this is equal to, first we've got the centrifugal force. Actually, let's start with the external force, F external. Now let's take out one by one. First, the centrifugal force. So minus omega cross r. Okay, that's the centrifugal force term. Then we've got the Coriolis effect term. Let me erase these pictures so I've got more space. Coriolis effect is of the form 2 omega r dot. Then we've got omega dot. Oh, by the way, there should be a mass in all of these terms. So, because obviously F equals ma, not A. So minus 2m omega cross r. And then we've got minus m omega dot cross r. That is our change in angular velocity term. Our displacement term now kicks in as m d squared c dt squared. And finally, our 1, 2, 3, 4, 5. Okay, that is all 5 of our terms. So let me make sure that I have written this correctly. External force, we've got our change in origin term. We've got our Coriolis effect right here. We've got centrifugal force right here. And finally, we have this is centrifugal force, and this is omega dot cross r. This is our Coriolis effect force over here. What is this? Omega dot cross r. Right, this is the change in angular velocity force. Okay, good. So we've got all 5 of our force terms accounted for. This massive beast is Newton's second law in our rotating reference frames. Okay, so now we're going to try to apply this to solve the Foucault pendulum problem. Okay, so now it's really going to be cooking things up, and so everything is going to be very nice and straightforward from now on. The calculation is going to be long, but the ideas will be straightforward from here on. So the first thing I'm going to do is claim that this term, the change in displacement term, is going to be 0, because I'm going to make my origin this point on the surface of the Earth. So there is no change in the origin effectively, because I've moved my origin to the surface of the Earth. So that means this term right here waves bye-bye, okay? So that term is gone. So this d squared c dt squared is 0. What other terms can we neglect? Any terms that have an omega dot can be neglected, because the angular acceleration of the Earth is, to a very good approximation, 0. So this term, due to the change in angular velocity, is 0. And let's see what other terms we have. Okay, we've got these two terms left over. Now, it should be noted that the Coriolis effect, let me make sure I've gotten this down right. Okay, so this right here, the centrifugal force, is actually going to be encoded in F equals mg. Okay, so it's going to be already accounted for when we write gravitational force. Okay, and that looks like it's about it. Okay, now we can write down Newton's second law in a rotating reference frame for the Foucault's pendulum. Okay, wonderful. So now let us write down Newton's second law for the Foucault's pendulum. First, let me draw a picture. Very good to always draw a picture. So here is x, y, z, and here is the support point for my Foucault's pendulum. Here is the mass, right? So here's the Foucault pendulum. And let me write down Newton's second law for my Foucault pendulum. So F equals ma, those are double dots, and that's equal to my external force, which is going to be mg, which already accounts for this centrifugal force. And there's also going to be a tension in the string, right? This string over here has some tension force that's pointing up. And gravity is, of course, perennially pointing down. And the tension force is going to be some vector. We'll figure it out. And then finally, we have our last term, which is due to the Coriolis effect, minus 2m omega cross r dot. So those are all of our terms for the Foucault's pendulum in rotating reference frames. So now let's go ahead and calculate them. First thing I'm going to do is write down each of these forces in vector form. So first of all, mg, let's start with the easiest one. So that's just gravity, and it's only going to act in the z direction. Okay, it's always pointing down. So you can see that my x and y components of the gravity vector are 0, and z component is mg. Okay, that's fine. Let's look at the tension force. Now the tension force vector might be a little bit tricky, you might think, but it's actually just spherical coordinates. So consider this. This angle right here, I shall call it phi, this angle theta. That means that to construct this tension force vector, observe that I need this much of the y vector, this much of the x vector, this much of the z vector. So my x component is simply going to be the x component in spherical coordinates as usual. So r sine theta cosine phi. Actually, that's my y component. That's my x component. Let me write it here so that I don't get confused. I don't want to confuse myself. R sine theta cosine phi. That is our x component for the tension force. And of course, it's pointing in the negative direction. So I'm going to write it as minus r, not minus r, minus t sine theta cosine phi. I'm actually, you know what, since we're already using theta for the polar angle of the Earth, right? We're already using theta for this angle. Let me call this something else. Let's call it psi. So let me call it minus t sine psi cosine phi. And then my y component is going to be, instead of r, I'm using t. So t sine psi sine phi. So this is going to be comma, hopefully you can still see what I write. So let me write it over here. Minus t sine psi sine phi. And finally, the z component is going to be t cosine psi. T cosine psi. This should be a t over here. So my z component is t cosine psi. Okay, very good. And that is our tension force. Let me make sure that I've written it down as I should. Minus t sine psi cosine phi minus t sine psi sine phi t cosine phi. Very good. So this is our tension force. Now the next step is to write down our last component for the force vector, which is our Coriolis effect. Yes. So I'm going to compute omega cross r. Now here's the little bit tricky part. First we have to determine what omega is, and then we have to determine what r is. So let's think about that for a sec. So here is the Earth, okay? Here is the axis of rotation, okay, of the Earth. And we know that the omega vector, the angular velocity vector, is pointing up, and the r vector is right. No, sorry, what am I saying? I'm not going to use r right now. So this is z hat, this is x hat, and we have to somehow express omega in terms of our Cartesian coordinate system right here. So let's think about how we can do that. Well, I can bring omega up over here, right? I can move it over here. So let me draw it. Let me draw the picture again over here. So here is omega. That's omega. Here is z hat. It's pointing radially outwards. Here is x hat, which is to the south. So now think about what I can do. What if I actually draw x hat in the opposite direction like this? So this is minus x hat, right? In the minus x hat direction. So the components of omega in the z hat is going to be this, and in the x hat is going to be this. So in the z hat direction, so let's think about what this angle is. This angle is our polar angle theta. So maybe I should write it here as well. So this angle right here is theta, right? This was omega. I just displaced it. So if this angle is theta, this angle had better be theta as well, since I just drew a parallel line by displacing omega. And so this right here, this component, sorry, that's not the component. The component of omega in the z hat direction is this much. So that is simply going to be what? It's going to be omega cosine theta. So that's in the z hat component, z hat direction. And likewise, for the x hat direction, if this is theta, then what do I know? This angle is also theta. So then this component of omega in the x hat direction is going to be minus omega sine theta. Why minus? Because I'm in the minus x hat direction. So very good. So now I've determined the components of omega in my Cartesian coordinate system. So I'm going to write it over here. Let's write it down over here. So omega is equal to, in the x hat direction, I have minus omega sine theta, and in the y hat direction, I have 0, and in the z hat direction, I have omega cosine theta. Okay, so now I can erase this diagram. It has outlived its use, and that's it. That is the direction, that is the omega vector. Okay, let's make sure that I've written down correctly. So omega is cosine theta z hat and minus sine theta x hat. Very good. So this is omega. Now I'm going to write my x vector or r hat vector. So r vector is simply going to be x, y, z. That means r dot is just going to be x dot, y dot, z dot. Very good. Now we're going to compute omega cross r dot, which is just a first grade calculation. So let's quickly compute the cross product here. And let me erase all of this. I don't need any of that anymore. So maybe I should take a different color. Okay, so omega cross r. Let's do it. Omega cross r dot. So I've got I hat, j hat, k hat. So omega, its components are minus omega sine theta for x hat, 0 for y hat, omega cosine theta for k hat. And r dot is just x dot, y dot, z dot. So now, hopefully you can still see, maybe I'll write it over here. since there's a lot of space. So let's write the results for the I hat, j hat, and k hat vector for this cross product. So for I hat, I've got 0 minus y dot omega cosine theta. And my condolences to you if you can't follow at this point, because if you can't compute a cross product at this stage, then well, quite frankly, you shouldn't have made it that far. So minus omega z dot sine theta minus x dot cosine theta omega. And k hat, we've got minus y dot omega sine theta. So that is all of our components. Let's ensure that I didn't make any silly mistakes. So I've got z and y dot omega cosine theta. For j hat, I've got minus z dot omega sine theta, and then minus x dot omega cosine theta. And for k hat, I've got minus y dot omega sine theta. Okay, very good. I believe I've done it correctly. So now we can go ahead and start summing everything up. We can sum up all of our forces to get the total net external force, the total force acting on the Foucault pendulum, period. So let me switch up the colors. Let's use yellow here. So my total force vector, F, is going to equal, well, mg. So mg is 0, 0, mg, right? Pretty straightforward, I suppose. And what about T, our tension force? That is minus T sine psi, cosine phi, comma, minus T sine psi sine phi, comma, T cosine psi. Very good. That is our, what is that? That's our tension force. And then we have minus 2m omega, whatever. So let me actually factor that out. So minus 2m. I know it's a minus, but I'm going to distribute out the minus sign in a moment. So, and let's factor out the omega, because, yeah, there's an omega everywhere here. So after I go ahead and distribute the minus sign, I'm going to have y dot, I factored out the omega, y dot cosine theta, comma, z dot. So got to be a little careful here. Maybe I'll keep the minus sign here and I'll distribute it afterwards. So this is minus. Here I've got z dot sine theta and plus x dot cosine theta, and then comma minus y dot sine theta. And now I am in a position to distribute out the negative sign. So this will become positive, this becomes negative, this becomes negative, this becomes positive. So I should have everything correct here. Let me ensure that I've not made any sillies. So my tension force is 2, where's my tension? Okay, here's my tension, minus T sine psi cosine phi, very good, minus T sine psi sine phi, good, T cosine psi, good. This looks great, 0, 0 mg, this is great. Okay, let's take a look at this, 2m omega y dot cosine theta, okay, minus x dot cosine theta minus z dot sine theta, y dot sine theta. Okay, great. Now we can just add all of these up to get our total force vector. So let me erase these diagrams here. Oh, is that my chalk? No, someone else's chalk, so it does not matter. So let's erase all of this and write down what we have just computed. So I've erased everything except my total force. So my total force vector now can be written as, what can I start writing? Let's start writing here. My total force vector can now be written as, so this x hat component is 0 plus this times 2m omega, of course. So I've got minus T sine psi cosine phi, okay, plus 2m omega y dot cosine theta. That is my x hat component. Moving on to y hat component, 0 plus this plus all of this. So I've got 0 plus minus T sine psi sine phi, and minus z dot, or actually let's start with x dot since it's what I've got in my notes, minus x dot cosine theta minus z dot sine theta. And finally, I've got t cosine psi plus y sine theta. Okay, very good. That should be my total force. Let me make sure I've got it down. So minus t sine psi cosine phi plus 2m omega y dot cosine theta. Same thing here, but with sine phi. And did I miss? Yes, this is why I check my work. I missed a factor of 2m omega when copying down this term. So there should be a 2m omega accompanying all of this. So 2m omega times x dot cosine theta. So now if there's a minus that I factored out, there should be a plus here. X dot cosine theta plus z dot sine theta, all times 2m omega. And finally, y dot sine theta plus, something's wrong here, y dot sine theta plus t cosine psi plus mg. So I forgot my plus mg term, plus mg. Okay, very good. So that is our total force. So now I can erase this finally. Okay, good. So now we can write down the force. Now we just want to analyze the motion of the Foucault pendulum on the xy plane. So I'm actually going to neglect its motion, neglect the motion of the Foucault pendulum on the z axis, okay? Because we're just focusing on how it looks, how it's oscillating on the xy plane. So if I focus on that, then I can write down that in the xy plane, so the x component has an equation of motion given by this. So minus t sine psi cosine phi plus 2m omega y dot cosine theta, and my double dot is equal to minus t sine psi sine phi minus 2m omega x dot cosine theta plus z dot sine theta. And I'm not going to write down z double dot because I'm making, first of all, I'm neglecting to look at the oscillation in the z direction because, first of all, I'm just to justify that quickly, under small oscillations, the amplitude of z dot is much less than x dot or y dot. You can think of that physically as saying that when the oscillations of the Foucault pendulum is small, then it does not really move in the z direction. Rather, it mainly oscillates back and forth on the xy plane, right? But it does not really change its z component, okay, for the pendulum, right? So that's the approximation we're making to neglect z dot under small oscillations. Small oscillations being when theta is near zero, but obviously not, very close to zero. Maybe it could be theta is near 10 degrees, less than 10 degrees, or 15 degrees. So that allows us to neglect this term that has a z dot. Okay, neglect that term. It's negligible under our small angle approximation, under our small oscillation approximation. So then we have these two equations of motion for the Foucault pendulum in the x and y directions. And so now we can start talking about something else. So remember that in spherical coordinates, right? In spherical coordinates, we had that r is equal to, x is equal to r sine psi cosine phi, and yes, right, not r, actually, we used L, where L is the length of the pendulum. And likewise, y is equal to n sine psi sine phi. So that means if I just solve for x over L, well, x over L is simply sine psi cosine phi, and likewise y over L is sine psi sine phi. So that means I can replace this sine psi cosine phi with x over L and replace sine psi sine phi with y over L. And likewise, I can make one additional, not approximation, this was exact, but one additional comment is that when we have small amplitudes for our oscillation, let's say you have a pendulum like this, right? Then it's not really small amplitude. But If the pendulum is very close to vertical, then you can imagine that the tension force T is exactly balanced out by the gravitational force mg, and in fact that they would be equal. So we can replace this tension force T, its magnitude can be replaced by mg. And likewise here, T can be replaced by mg. And so now I can rewrite all of this as follows. I can write mx double dot is equal to minus mg, replace all of these trigonometric terms by x over L, plus 2m omega y dot cosine theta. Here I have my double dot is minus mg, replace all of these terms by y over L, and then I have minus 2m omega x dot cosine theta. And now I can simply cancel out my factor of the mass, and now I have the equations of motion of a Foucault pendulum. To solve a couple differential equations like this, first of all, notice that x double dot depends on y dot, and y double dot depends on x dot. So somehow they're tangled up, they're tickling each other, and somehow we have to deal with that. Somehow we have to solve the problem, taking that into account. So what I'm going to do is I'm going to introduce a variable z, which is a complex variable made out of x plus iy. Okay, so that z double dot is x double dot plus iy double dot. And I'm going to try to solve this differential equation instead of these two coupled differential equations. So let's see if that helps us at all. So first of all, what is x double dot? X double dot is just this, right? It's g x over L plus 2 omega y dot cosine theta. That's x double dot plus I times y double dot being minus gy over L minus 2 omega x dot cosine theta. Right. So now I can just factor out common terms. So let's factor out g over L. That gives me x minus iy. Is that right? X minus iy. Shouldn't it be x plus iy? Maybe I've overlooked something. Maybe a factor of I is missing here. So let's take a look here. So z double dot should be minus g over Lx. Did I? Oh, there's a minus sign here that I forgot to write. So that's a minus sign here. So this should be minus x minus iy. Factor out that minus sign. Make this plus. Make that plus. So very good. And now I'm going to write my second term. So 2 omega cosine theta. And now if I factor that out, I'll have a y dot. So y dot minus x dot, I suppose, minus ix dot. Now that looks kind of backwards from x dot. Now let me just write z dot here. Z dot is just x dot plus y dot. So this is a little bit different than z dot, but now notice if I introduce an I over here, right? If I introduce an I over here and make this a negative sign, right, what happens? Well, then this I will multiply with, okay, let me do it out. So I'm going to have minus I squared here, which is going to be positive 1. That's going to give me x dot. And then I'll have minus, or rather, plus iy dot, okay? Let me make sure I've been ethical with my signs. I don't want to do anything unethical. So we've got minus 2I omega cosine theta, x dot plus iy dot. Okay, very good. So that should be correct. So this can be replaced by z, right? And this we can replace by z dot. Okay, so then our equation of motion now becomes z double dot is equal to minus g over L times z minus 2I omega cosine theta times z dot. Okay, so this is our new differential equation. Z double dot is minus g over L z minus 2I omega cosine theta z dot. Okay, very good. So now we're going to try to solve this ODE, and you can see it's much better than the previous two coupled equations we had, right? Because this actually looks decent. We can actually have a shot at solving this. In fact, our shot is going to be very decent at solving this. We're going to conjecture that the answer is of the form e to the minus I alpha t. Okay, let me make sure we've got the ansatz correct. Good. So making this ansatz, then z dot is simply minus I alpha e to the minus alpha t, or minus I alpha z. And likewise, z double dot is minus I alpha squared e to the minus I alpha t, or minus I alpha squared z. Okay, and actually, let's simplify this further. This is going to be I squared minus alpha squared z. Okay, now let's go ahead and plug that in here. So z double dot can be replaced with minus, let's just go the full way here, minus alpha squared e to the minus, actually no, minus alpha squared z. Let's keep it z, it's going to get canceled out anyway. So it's equal to minus g over L z minus 2I omega cosine theta times z dot, where z dot is minus I alpha z. And so now observe that all our factors of z cancel out as predicted. So I have minus alpha squared is equal to minus g over L minus 2I omega cosine theta. Now minus minus makes plus, and I've got two factors of I, and I've got an alpha. So that gives me minus alpha squared is minus g over L minus 2, let's see, minus 2 omega cosine theta times alpha. If you take a look at this, we've got an alpha squared here and an alpha here, hinting these two orders of alpha, these two powers of alpha, hints there's probably a quadratic equation going on here. So let's see. Let me bring over alpha squared to the other side. Maybe move over here. Okay, so I've got alpha squared. Hopefully you can still see this. So alpha squared minus alpha times 2 omega g over L times cosine theta. And I've got a constant term of minus g over L as well. Okay, very good. Oh, that constant term is completely different. Oh, so that's actually just minus 2 omega cosine theta. And then my constant term is minus g over L. Okay, so alpha squared, okay, minus 2 omega cosine theta times alpha, and minus g over L. Okay, simple quadratic, trivial to solve. So I've got A is 1, B is minus 2 omega cosine theta, C is minus g over L. So here alpha is going to equal minus B, so that's going to be 2 omega cosine theta, plus minus the square root of B squared, which is 2 omega cosine theta squared, minus 4A, which is 1, times C, which is minus g over L. All over 2A. 2A, of course, is simply 2. So that means alpha has two roots, right? It has a positive and negative solution. And that's going to be 2 omega cosine theta plus minus the square root of 4 omega squared cosine squared theta plus 4g over L, all divided by 2. Dividing top and bottom by 2 gives us omega cosine theta plus minus the square root. Now I can pull out the square root of 4, giving me 2, leaving me with square root of omega squared cosine squared theta plus g over L. So these are our two roots for alpha, and hopefully I'm not mistaken in that. Omega cosine theta, omega, okay, very good. And so now finally we can conclude with the final solution for the equations of motion of the Foucault pendulum, which comes in two flavors. We've got the positive root for alpha, so it's going to give us a e to the minus I times omega cosine theta plus the square root of omega cosine theta squared plus g over L. Okay, all of this times t, and then plus b times minus I to the, now we're going to have the negative root. So the exact same thing, omega cosine theta, but with a negative. So minus omega cosine theta squared plus g over L, hash that, and that, times t. And this, ladies and gentlemen, is the final solution for the equation of motion for a Foucault pendulum. And we are done. So that is it for this lecture of class. Wow, I have so much chalk on my hands that clapping them actually released a fog cloud. But that is it for this lecture. This is the conclusion of the lecture. We have completed, derived the equation of motion for a Foucault pendulum in rotating reference frames on the Earth. And that is it, and we will see you in the next one.